Hey everybody. Today we're talking about the law of total probability, which computes the probability of an event by splitting it into disjoint parts and then adding the probabilities of those parts. I'm not going to talk about this formula just yet. I want to build up to it because it's a lot to absorb all at one time, I think. Let's start with an example. Flip a fair coin. If the result is a head, roll a 6-sided die. If the result is a tail, roll an 8-sided die. What's the probability of the event? The roll is a 1. This event can happen in two different ways. You get a head and then a 1, or you get a tail and then a 1. And those two events, H1 and T1, are disjoint from one another. So what we're going to do is going to find the probability of H1, the probability of T1, and then add those together. We then compute the probability of H1 and T1 using the multiplication rule. So we take the probability of a head and then multiply by the probability of getting a 1, assuming that we got a head. Similarly, for T1, we take the probability of a tail, 1/2, and multiply that by the probability of getting a 1 in the case where the coin flip was a tail. After a little bit of simplification, we get the probability of E is 7/48. The situation is represented by this picture, where the shaded area represents the event E. You can see that the larger square is divided in half. We've got head on the left and tail on the right, and some of event E is in the head section and some of it is in the tail section. More formally, the event E can be written as the union of head intersect E and tail intersect E. A partition of a set S is a collection of non-overlapping subsets that together cover all of S. If we call those sets B1 up to BR, then the intersection of any two of those B's is going to be the empty set, assuming that the two B's are different from one another. And the union of all of them together is the sample space, is S. In the last example, the events H and T, a head on the coin and a tail on the coin, partitioned the sample space. When B1 up to BR, all those sets partition the sample space of a probability experiment, any event E is then partitioned by E intersect B1, E intersect B2, etc. And again, this picture is illustrating that. And you can see how on the left, B1, B2, B3, and B4 split up S. On the right, E intersect B1, E intersect B2, etc. split up that set E. The law of total probability describes the probability of an event in terms of the partition, B1 up to BR. In particular, we can write the probability of E is the probability of E intersect B1 plus the probability of E intersect B2, etc. We can write that in summation notation. And then finally, we can write the probability of the intersection in terms of the multiplication rule. So the probability of E intersect BI is the probability of BI times the conditional probability of E, given that BI was the case. Another example. A company has this data on customers entering a store. They have the age groups of the people that have entered, the percentage of the people that entered that are in each of those age groups. So, for instance, 24% of the people entering are below 25 years old. And for each of those age groups, they have the probability that someone in that age group makes a purchase. So, for instance, someone below 25 has a 37% chance of making a purchase in this store once they've entered. We'd like to compute the probability that a randomly selected customer makes a purchase under the circumstances where we don't know anything about their age. In order to do this, we're going to use the fact that these four age groups partition the sample space, and that will let us partition the event E, the customer makes a purchase, and then we'll be able to apply the law of total probability to that event E. In particular, the probability that they make a purchase can be broken down into four pieces. The probability that they're under 25 and buy, the probability that they're 25 to 45 and buy, etc. All of the events listed in those parentheses there are disjoint, so these probabilities add directly. We evaluate each one of those probabilities using the multiplication rule. So for instance, the probability that they're under 25 and buy is the probability that they're under 25, which is 24%, times the probability that they buy given that they're under 25, which is 37%. We do all this arithmetic, we simplify, we get 26.2%. One more example. 2 cards are drawn from a standard deck without replacement. What's the probability that the second card drawn is a heart? We're going to do this problem by partitioning the sample space using the outcome of the first draw, and then applying the law of total probability using that partition. Let B1 be the event that the first draw is a heart, and B2 be the event that this first draw is not a heart. There are 4 suits with equal numbers of cards, so the probability of B1 is 1/4 here, and the probability of B2 is 3/4. Now the event we're interested in is that the second draw is a heart. We'll call that E. And we're going to compute that by finding the probability of E and B1, the probability of E and B2, and adding those up. In order to evaluate those probabilities of those AND statements, we're going to need the conditional probabilities of E given B1 and E given B2. So, the probability of E given that B1 has happened is 12 and 51, because if E has happened, or rather because if B1 has happened, the first draw was a heart, so there's only 12 hearts left. One of the cards is gone, there's only 51 cards left. Similarly, the probability of E occurring when the first draw is not a heart is 13 and 51, because this time there are 13 cards left in the deck that are hearts. By the law of total probability, the probability of E is the probability of B1 times the probability of E given B1, plus the probability of B2 times the probability of E given B2. Plugging in all those probabilities, simplifying a little bit, we get 1/4. The probability that the second draw is a heart is exactly the same as the probability that the first draw is a heart. And it turns out that the probability that the third draw, the fourth draw, the fifth draw is a heart is always 1/4.